Can you hear me?
Yes, we can hear you great.
Okay, thank you. This is joint work with I am Marcio Adames. This is joint work with Francisco Ganassin and Andrés Teclain, and we made simulations of geometric aspects for Arapuca designs. A short overview of the talk. I'll give a very brief introduction to Dune and how our simulations fit in Dune. And then these presentations consist of a summary of 4 small works. We considered putting slits in the wavelength shifting plates to see how this affects the efficiency. We considered size comparisons, comparing, we will see X Arapucas of different sizes to see how this changes the efficiency. And for rectangular Arapucas, we considered the lateral positioning of SIPMs, and in the end, a supercell versus megacell comparison. So for the introduction about Dune, this is related to Dune's fire detector. Dune seeks to study neutrino interactions. There will be a powerful neutrino beam produced at the LBNF. This beam will pass through the near detector towards the far detector. And in the far detector, there shall be these large liquid argon chambers. They are large TPCs. There shall be four modules. The photon detection system of Dune far detector is based on Arapuca technology. Here I have an image from the Dune TDR of an exploded single cell. This would be the smallest possible Arapuca. A single cell, a photon comes through the dichroic filter, gets to the wavelength shifting plate, changes its wavelength, and then gets stuck inside the Arapuca and shall be bouncing here until it reaches an SIPM, or at least that's what we would like. And but this design works. This is a proof design. And here I have an image of a very specific Arapuca design. It's called the supercell, and the first module of the fire detector shall be based on the supercell. The supercell, each of these rectangles is a dichroic filter, so it's a 6x1 Arapuca, X Arapuca, and we shall talk more about this later. For the second module, the design of choice shall be the X Arapuca megacell. Here, this is not an up-to-date image, but shall be a 6x6 Arapuca with 36 dichroic filters on each side for the double-sided, or on a single side for the single side, with SIPMs on the edges. And our simulation studies are important for the optimization of the device for the second module. The second module has many different aspects in comparison to the first module, and we study how these Arapucas should behave in this new environment. About our simulations, we designed a Python model that creates the geometry for the simulations based on several parameters such as size of the detector, number of SIPMs, heights, lengths, and other parameters. The physics of the photons inside the X Arapuca is simulated by a ray tracer using a C++, written in C++, using an uniform grid as an acceleration structure. And our simulations focus on reflection and refractions using Snell's law on the interfaces, and total internal reflections inside the wavelength shifting plate that absorbs every incoming photon and re-emits it in a random direction. So our simulations are an ideal case, and we are interested in see how they compare to each other, trying to define how changing a single parameter might change the efficiency. Our studies do not intend to find in a very accurate overall efficiency. And the advantage in doing the way we do this is that we can test hundreds of different designs and run them in a viable time. And the purpose of our studies is to compare the collection efficiency of each Arapuca designs for different parameters. So when a photon comes inside an Arapuca, it comes towards an Arapuca, it goes through the dichroic filters to the acceptance window. And this is the acceptance efficiency, which we are not simulating. Our photons start at the end of the acceptance window. And then we simulate the geometric aspects of how they bounce inside the Arapuca. So this is the collection efficiency. We are trying to optimize the geometric parameters to find how they should reach more easily as IPMs. Here, this is an image of an X Arapuca of a 4 mm thick light guide. This is a 6x2 design with SIPMs on the sides here. Each SIPM is a 6x6 mm square. And here we simulated all such X Arapucas with from 1 to 16 SIPMs per side of the dichroic filter. So each of the exposed sides has from 0 to 16 SIPMs, and the efficiency, the collection efficiency we get for these designs is marked by these points here. So we see as maybe expected increased efficiency, but with diminishing returns. So we consider the possibility of having an horizontal slit in the light guide, so making a horizontal slit through the side of the light guide to see if this increased efficiency. This is an idea that was explored also by Gustavo Valdivieso. And our results are these. Each of these colors represent a depth for this slit from 0, no slit, up to 7 mm deep. And this is the curve of efficiencies. And we also considered increasing the heights of the Arapucas. So this simulation, we should be seeing these graphs move as we increase the height of the Arapuca. So as we increase the height, we see that we get smaller and smaller efficiency, and the ones with bigger slits are the ones that suffer more. I'm sorry. So maybe indicating that these horizontal slits will not help very much for our parameters, for our choice of parameters. We also considered vertical slits, so cutting vertical slits in front of the SIPMs, trying to make them leave the Arapuca more easily. And our results show something very similar. The one without slits do better than the others. And in a similar video that maybe we show that as we increase the height, we get lower and lower efficiencies. So we should not be making very thick Arapucas. Another study, we considered X Arapucas of different sizes. So each of these dichroic filters is a 10 by 10 centimeter square. So this one is 60 by 60, and this one is 10 by 10 by 10. And we have 4 SIPMs per acceptance window. So this means that this one will have one on each side. But this one, we don't have sides here in the middle exposed. So this means that we'll have 2 SIPMs on each exposed acceptance window side. 3, 4, 5, and 6. And we try to see how these differences show in how how the efficiency differs in these cases, and we get these results with one dichroic filter about less than 20% collection efficiency and up to 36. The 6x6 has 36 dichroic filters. We get up to 35% or something. This blue line here is the logarithmic best fit of the square Arapucas, and we also plotted here the efficiency with the calculated number of SIPMs for the 6x2 and the 6x3 Arapucas, and they go worse than the square Arapucas. We also considered for rectangular Arapucas the possibility of having positioning SIPMs on the 4 sides, on 2 longer sides, on 2 short sides, or on a single short side. So if you have, for example, 10 SIPMs, how should you allocate them? Should you put them, divide them equally on the 4 sides, or allocate all of them on a single short side? And the efficiency graphs we have here, this red line is for allocating on a single short side for a 6x2 Arapuca. For this case, we can fit only only 32 SIPMs on a single short side. So we would have a nice efficiency, but limited by the side. And for the other cases, dividing them equally on the 4 sides does better than allocating more of them on a single short side or on the longer sides. We made the same study for the 6x3 X Arapuca. 4 sides, short sides, longer sides, single short side, and we get a similar result. We should be allocating them on, divide them equally among the 4 sides. Last but not least, in the end, we have this Arapuca supercell. This is the design for the first module. The supercell is a 10 by 80 centimeters, 6 times 10 by 8, side by side here, with 48 SIPMs, 24 on each side. This makes to 1 SIPM to each 10 square centimeters of active collection area of acceptance window area. And our simulated collection efficiency goes to 33.7%. And for a very, very rough estimate, we just use numbers from other works, from other people, that this acceptance window efficiency should be about 34.5%, and the SIPM efficiency should be something about 45%. And this would indicate a rough estimate of 5.2% for the overall efficiency of the supercell. For the mega cell, for the second module design, it is a 6x6 with 10 by 10 square dichroic filters. It has 160 SIPMs, but it's much larger. This makes to 1 SIPM.
Sorry for interrupting. You're up to 14 minutes, Marcio.
Okay, okay. So this makes 1 SIPM to each 22.5 square centimeters of active area, and we get a collection efficiency of 41% to a rough overall efficiency of 6%. So comparable to the supercell, but using less SIPMs per active area of collection. And our conclusions is that our simulations indicate that X Arapucas of smaller height are more efficient. that vertical or horizontal slits do not increase efficiency at 1 millimeter distance for the wavelength shifting slab to the SIPMs, at least. That larger square-shaped X arapucas are more efficient than rectangular ones. However, they provide smaller spatial revolution if you make your arapucas too big, then you don't know where in the arapuca the photon hit. And for rectangular X arapucas, it's better to allocate the same number of SIPMs per side, but shorter sides have better efficiency than longer sides if we have to choose between them. So we thank Ana Machado, Héctor Segredo, Gustavo Valdivieso, Flávio Cavanha, and Laura Paulucci for help in several stages of this work. And that's it. Thank you very much.
Thank you for the excellent presentation. We have time for one quick question, maybe, if somebody's ready. Maybe I can ask a quick question. So you wrote a standalone simulation framework in Python. Do you have any interface with GM4, or is this completely standalone?
It's completely standalone. Gen4 does incredible simulations, but we find difficult to use it to make the number of different designs that we need. So we designed this module, and it represents an ideal simulation, an ideal case, but we are working to make it more, to include more physical aspects into it.
Thank you. Let's move on to the next speaker. If you could stop sharing, that would be great. And
thank you very much.
Thank you. The next speaker is Dante Totani, and he's going to talk about timing resolution in microburn photon detection system. Are you able to share? Yes.
Okay. Hello, all. Can you see my screen? My slides?
Yes, looks good.
Okay. In this
I'm
slides,
going to try different and say a 10 minutes wave to you and say you have 10 minutes.
Okay, thank you. In these slides, I will show the analysis steps that bring to a demonstration of nanosecond timing resolution in the microburn photon detection system. The microburn is a neutrino experiment at Fermilab sitting on the booster neutrino beam and measuring GeV neutrino interaction. The aim of this analysis is to improve the neutrino beam event timing resolution at level of few nanoseconds. Using PMT signals, the beam structure is reproduced at level of nanoseconds or few nanoseconds, and an estimation for the detector timing resolution is obtained. As a reference for the beam structure is used the signal from a resistive wall monitor is used as comparison for the event timing. The RWM gives us a waveform which describes the protons bunches inside the 1.6 microsecond pulse, and which is arranged in 82 bunches with a certain separation between them, that is 18 nanosecond or 52.81 megahertz, and each single bunch has 2 nanosecond wide. So an analysis overview. This analysis, what I am using is muon neutrino charge current filtered BMB events. So neutrino from beam. The waveforms are picked up from 31 PMTs, and the RWM signal are taken into account, and the timing of both waveforms is obtained from the half-8 of the rising edge with a resolution of 0.2 nanoseconds for each single waveform timing. Then the step of the analysis is to apply correction to the event timing. The first one is trigger correction based on RWM signal. Then we use the reconstructed neutrino vertex coordinate to determine the neutrino path before the interaction and the gamma, the scintillation light path from the scintillation point to the PMTs. And once the two paths are determined, correction for the neutrino and gamma time of flight are applied. And finally, from the 31 PMTs, the timing, to each event is assigned a timing with certain criteria that essentially are the average of the PMT fired. Just the things the PMTs are 32, but one is dead. So this is the reason because I tell 31 PMTs. The timing correction, three main sources for the event timing jitter are identified. So starting from the top, when there are no corrections, there are no beam structure. But after the first correction applied, which is the RWM correction for the trigger, which introduces a 100 nanosecond jitter, the beam structure starts to appear. Then the correction for the neutrino time of flight and the gamma time of flight, which are both of the order of 30 nanoseconds, the beam structure starts to be more and more defined. So once a certain beam structure is reached, a fit with a three-Gaussian function is made, and further correction are applied based on the mean of the central Gaussian. The two main second order correction applied are the first one, looking at the PMT by PMT, a certain offset is observed and is removed. And the second correction is made based on the position of the interaction vertex. And from this analysis, we figure out that some closer events with the vertex too much closer to the PMTs present some deviation from the expected behavior. As for events where the vertex is very far, we think that this is a problem due to the fact that we are using the vertex for the light source. When we know that the really light source is not from the vertex of the interaction, but it comes from the daughter particles, so in a region that is not point-like, but is an extensive region of argon in the TPC. So this stuff is still working in progress, but soon there will be more things about this kind of analysis. Once all the corrections are applied for each event, from the 31 PMT, only PMTs fired with more than 2 PE are considered. When I tell 2 PE, I mean the amplitude of the fast component is larger than 2 PE. And the second step is removing outlier from this group of PMTs fired. And to remove the outlier, I applied a robust statistic method using the median and the MAD. And I chose this cut that is a bit arbitrary, but this is equivalent to preserve 95% of the good events telling. And finally, to each event, the timing is assigned as the average PMT, the average timing from all the PMT that passed this selection before. After this selection and this, the remaining data set has been fitted with a three-Gaussian function again. And the spread, actually this three-Gaussian function, the three Gaussians has the same parameters. So the sigma is common to the three peaks, and obtaining a sigma of 3.09 nanoseconds, which is associated to the resolution of the whole data set. And moreover, there is a second parameter that is a flat term, which represents the background from cosmic events, which is flat, and from this fit is obtained to be 26%. That is compatible with the expected amount of background from the NuCC selection. So with this kind of resolution, we were able for the first time in microboon to reconstruct the beam pulse nanosecond substructures. And here there is just a flash of the full data set reconstructed in time with using the PMTs. And a further analysis done on the resolution, since the one obtained is inclusive for the full events dataset, and moreover, the beam spread is included in this 3.09 nanoseconds. Since the WM give a very well resolution for the protons structure, we can measure a sigma for the beam an intrinsic beam sigma of 1.31 nanoseconds. And so we can remove in quadrature these contributes. At the end, the intrinsic sigma of the detector for the full dataset results to be 2.8 nanoseconds. Again, this is for the full dataset. If we explore the sigma versus some quantity, as in this case, we explore the sigma versus the number of photons detected per event, we have this kind of behavior, and we can observe that for events with large number of photons, the sigma, the spread in timing reduce, and we have a limit for very large number of photons detected of 2.2 nanosecond resolution. Okay, with this kind of resolution, the beam event timing can be exploited to improve the cosmic background rejection in beam neutrino events. Based on the time distance from a beam pulse, as you can see in the picture here on the bottom right, one can define a probability of each event to be a neutrino correlated with the beam or a cosmic background coming from the flat contributes from a random in time background. In this example,
10 minutes warning.
Okay, thank you. In this example, I chose a window of plus minus 5 nanoseconds around the beam peak, that is represented by the two red lines. And in that case, as you can see, the cosmic background is removed at 50%. Instead, the beam neutrino events are preserved at 90%. So this is a proof that this analysis can be used to remove the cosmic background from beam neutrino events. So at the end, this work demonstrates the capability of microboon photodetector system to reconstruct the BMB nanosecond structure for the first time. BMB neutrino events time resolution is of the order of 3.1 nanoseconds, 3.09 nanoseconds. And but beside that number, the detector intrinsic time resolution achievable can be 2.2 nanoseconds, but further improvement are possible. And from these results, we demonstrate that a cosmic background rejection is possible using the timing of the events. Furthermore, the few nanosecond time resolution opens the door for searching new long-lived particles as we develop a light-based trigger system for future large TPC experiments, as SBND or DUNE. Thank you for your attention.
Thank you so much. This was a very interesting talk. Are there any questions for Dante? Oh, you guys are quiet today. So I will ask a question and then see if somebody else wants to chime in. You kind of prevented my question, which was, what are the applications on getting better timing resolution for other detectors? So maybe you can tell a little more about that. Okay,
the first application is actually, in particular, when we are looking at the event from beam, one can, as I told you, the first application that I immediately applicate is to reject a cosmic background, since once someone knows the beam structure, you can tell if this event is correlated or not with the beam. And secondly, these things that is still actually it's not applicable now, but it could be things to search in future analysis for long-lived particles as neutral leptons, since they can take some nanoseconds of delay to decay, and you can observe some asymmetry in the peak of interaction. So you can investigate events that are located in an asymmetric position, actually in delay with respect to the main peak of nuclear interaction.
Great, thank you for explaining. Other questions for Dante? Okay, if not, we can move on to the next speaker. The next speaker is Wei Mu from Fermilab. And where is Wei? Would you like to share your slides? Hi.
Hi, Maria. Do I share the red screen?
Yes, we can see your slides and we can hear you clearly.
Okay, thank you. Hi, hello everyone. This is Movie from Fermilab. Today, I will show our recent work related to the photon fast simulation based on machine learning algorithm. As we know, we can simulate photon transport using Gen 4, but it becomes challenging for photon-scale detectors with GeV level energy deposits, such as liquid argon detectors for neutrino physics. There are several methods to speed up photon simulation, such as using a lookup table or using a semi-analytical model that is presented by Patrick on Tuesday. There is another possible solution is to use a machine learning-based generative model. In general, the generative model is built on deep neural network and trained in the so-called GAN framework. However, based on our test, there are some problems with the popular generative model. First, the deep neural network architecture can be too slow when deployed without GPUs. In addition, the GAN framework relies on human eyes to determine the performance of the generative model, and it results in an unstable training procedure. Then, to address these two concerns, we developed a general network architecture for the generative model and proposed a clearly defined loss function for the model training. In fact, before reviewing the network architecture, let's think about the common photon detection system of a liquid noble gas detector. In general, the photon detection system consists of a series of photon detectors distributed in arrays and deployed on the walls of the detector. Photons emitted from a vertex where a particle deposits energy will illuminate specific photon detectors and form a heat pattern on the photon detection system. If we consider a liquid argon detector in a 3D Cartesian coordinate system, we can assume photon detectors are deployed on the YZ plane in an array. And it is reasonable assumption that the number of the detected photon by particular photon detectors depends on the distance to the scintillation vertex. That is the expectation of the scintillation point. And the distribution of the illuminated photon detectors in the YZ plane is determined by the YZ position of the scintillation vertex. Therefore, here we developed a feed-forward neural network, which has 3 input neurons on 3 input layers. The 3 input layers corresponding to the 3D position of the scintillation vertex, the X, Y, and Z. The neuron X shows the distance to the photon detection array, and it can be used for the light intensity normalization. And the position Y and Z are used to predict the detection probability along the column or the row on the photon detection array. And then the outer product of these 2 layers will form the heat pattern on the photon detection system. After that, we multiply the 2 layers, the intensity and the heat pattern, then we get a multiply layer that shows the photon distribution on the photon detection system. At last, the output layer shows the photon detection probability. In fact, some optional layer can be introduced to improve the prediction precision. Here, I would like to emphasize this shallow neural network uses the outer product layer to generate features instead of the widely used the upsampling layer or the transport convolution layer. Then it makes the generative model lightweighted and increases the inference speed significantly. In addition, the data structure used by this network can be organized in completely 1D dimension, and it makes the training of the network relatively easy. So it comes to the second concern, the training of the network. As we know, it is difficult to find a good metric to compare the similarity between 2-dimensional images. That's why many 2D generative models are trained in the GAN framework. As I mentioned in previous slides, the model proposed by us uses one-dimensional data structure. It makes it possible to find the clearly defined loss function for the network training. Motivated by the KL divergence, we propose a loss function in this form. Here, Px and Qx are true or test distribution of the detection probability on the photon detectors. This loss function, if you see, is symmetric and it will well behave no matter whether Px or Qx is small or not. Also, because this loss function is value weighted by the difference between Px and Qx, it guarantees the model to converge to the optimal value. Based on our test, it works perfectly for the problem we want to solve. Now, the model training you see here is a lot, but it's less tricky. First, we build training sample. In general, that's light source in the detector, and then simulate the photon transport in Gen 4 to get the so-called true photon detection probability. And then we train the model use a learning rate scheduler. This scheduler resets the learning rate to its initial value every 1,000 epochs to help the model get out of potential center point. Here, we set an auto stop condition when the loss stops improving after 500 epochs. And therefore, the network training procedure needs no human inspection and it will be stable. Now, let's apply this general model to some specific detectors. Here, we apply it to protodune and the dune geometry. In the protodune geometry, there are two photon detection arrays, and they are deployed on two walls of the detectors. Then photon in between these two detection arrays can be detected. On each array, there are two types of photon detectors, including 29 bar-like detectors and 16 segmented photon detectors. Then in total, there are 90 photon detectors are deployed in the detection system. In the dune geometry, there are also two photon detection arrays, but they deployed on a single wall of the detector. Then photon from both sides of the detection array can be detected. All the photon detectors are the same type and symmetrically distributed on the array. In total, there are 480 photon detectors. Here, I would say, although the protodune photon detection system has less photon detectors, the case is more complex than the dune because there are two different types of detectors and the distribution is not so symmetric. Okay, let's evaluate the performance of the model. First, we set the expected feature. It is true that the photon detector will observe more photons when light source is closer to it. Hence, the probability of the photon detected by particular photon detectors, or here I call it visibility, that it will be higher. Consequently, the visibility of the photon detector reaches a peak when the light source moves towards it and reduces when the light source moves away. In addition, both the model prediction and the Gen 4 simulation are expected to see smooth variation in the total amount of light detected by the photon detectors when the light source pass by. Then to evaluate whether the model can learn the feature, we compose 3 light sources. These 3 light sources move inside the detector along X, Y, and Z direction. And we try to predict the visibility using models and the Gen 4 simulation. And for each condition, we study visibility from 3 photon detectors. The comparison is plotted in this figure, and we can see the visibility of the photon detection systems change smoothly when the light source move along X, Y, Z direction. And the result from the model prediction, then on the top, this one and also this one, they match the general trend of what is produced by the Gen 4 simulation, this one and this one. Okay, another important information we want to extract is the number of total detected photons. It can be used for event energy reconstruction. Here, we obtain the number of total detected photons from a scintillation vortex by summing up the number of detected photons on each photon detectors. Then we calculate the discrepancy between the two approaches for each vortex. Then the discrepancy are filled to one-dimensional histogram and fit to Gaussian function. Then the figure on the right shows the overall distribution and the Gaussian fit. And this one shows the difference between the predicted and the simulated value for slices in the drift coordinate x. Then we can see the model can, in general, reproduce the result from the gentle simulation. Because the number of the total detected photons is predicted by the one neuron normalization layer, then we would like to conclude by this test that normalization by the one neuron layer works. Okay, besides the number of total detected photons, we need the model to predict the photon distribution on photon detectors. Here, we plot the number of detected photons by each photon detectors to a one-dimensional histogram and compare the output from the gentle simulation and the model prediction. It shows both methods give similar photon distribution for both photon detection systems. Now, here I would like to see, although the photon detection system deployed in prototype geometry contains two different types of photon detectors, the model can learn features from the training samples, and it gives reasonable prediction. Then this test proves the outer product layer can be well trained with 1D data structure. Okay, the goal for our model is to be both precise and fast. So to measure the computing performance, we compare the model prediction and the gentle simulation in LabSoft framework and then run on Dune GPVM at Fermilab. Here we built light source use 200 MeV muons and 2 GeV electrons and the supernova neutrinos for the benchmark task. In this table, you will see the CPU time per event, per image of heat pattern, and per photons. We compare the gentle simulation and the model prediction. Since the model is lightweighted, the prediction speed is around 20 to 50 times faster than the gentle simulation. And it also keeps same level of details and also precision. Another important information we extract from the test is the model prediction runtime only depends on the complexity of the models. You see here, number almost same, while the gentle simulation runtime increased significantly with the detector volume. You see, prototype and Dune. Then the total CPU time for an event will be determined by the amount of photons and the detector volume for gentle simulation, and only by the number of energy deposit or the number of images along the particle track for model prediction. So it implies that the model prediction can be much faster at the expense of less detail of the particle track. So while the model already generates considerable excitement, it's possible to add more optional layers for higher precision, but the trade-off is the inference speed increase. So we conduct a study to quantify both inference speed and precision at a different level of network complexity. In particular, we construct models at 4 levels of complexity by introduce 1 to 4 additional dense layers as the optional layer. The comparison and this is the comparison and the comparison between the precision and the inference performance between these 4 models. So our observation indicates a balance between the inference speed and the precision must be found when we choose the depth of the network. As the model prediction runtime depends on the network complexity. We also benchmark the inference performance for photon detection system with different number of photon detectors. Then the metric shown in this table reveals the inference time increased somewhat linearly with the number of photon detectors, but the model still outperforms gentle simulation at least by a factor of 10, even when there are 1,920 photon detectors are deployed in Dune geometry. Then, to summarize, here we propose a novel generative model for photon detection probability prediction. Then this model uses the outer product layer to predict the photon distribution and use a single neuron to normalize the photon intensity. And this architecture realizes the deconvolution from the scintillation vortex to the photon detection probability, and that makes the model prediction precise and fast. Then for detail, you can see our preprint on arXiv. And the model built for Proto-Dune demonstrates this neural network is able to learn features from training samples with 1D data structure, and even that for complex photon detection system. And the sample for the Dune photon detection system indicates the model gives fast and precise prediction of the photon detection probability. Then it proves it can be a powerful new tool for the photon fast simulation. For our future attention, we'll focus on incorporating the most recent cutting-edge neural network architecture to improve the prediction precision and the inference speed. Then we will also develop new photon simulation strategy, then using model according to physics goals for neutrino or dichromatic experiments. That's it. Thank you.
Thank you for the very interesting presentation. Are there any questions from the audience? You guys are letting me ask. Oh, there is a hands up. There we go. Micah.
Yeah, thanks for the great talk. I think you said something about comparing someone else who's doing similar, trying to achieve a similar thing with a light mapping technique or something like that. Can you comment on, if I'm getting that right, can you comment on how this compares to that?
Here, in fact, here, I mean, the comparison, because we use the 1D data structure and the output will complete 1D and we can fill into the 1D histogram. Then we can use some statistical metrics such as chi-square distance or Euclidean distance to compare between different models.
Right. I guess I was just wondering if you've done that.
Yes, I have a module that can do that.
Okay.
Yeah.
Thank you again for the great presentation. If there aren't any other questions, maybe we can move on to the next speaker. If you could kindly stop sharing. The next presenter is Anders Simon, who's going to talk about boosting background suppression in the next experiment. Do we have Anders? Yes, I see you. Would you like to share your presentation?
Okay.
This looks good.
Okay. Hi, everybody. I'm Anders Simon.
You're very faint. Your audio is very faint.
Okay. I'll hold my mic closer to the... Can you hear me now better?
Still a bit faint.
Sorry for that. Well, I'll talk louder.
Oh, that's much better.
Okay, okay, I'll go with it. Okay, so I'm Anders Simon. I'm a postdoctoral fellow in Ben Gurion University in Israel, and I'll give you a brief overview of how we are using Richardson-Lucy deconvolution to boost our background suppression in NEXT. NEXT is an international experiment that aims to detect neutrinos double beta decay in xenon 136, and to do so, we make use of a high-pressure gas TPC filled with xenon enriched at 90%. We are running at the Laboratorio Subterráneo de Canfranc in the Spanish Pyrenees. I know most of you already know enough about TPCs, but anyway, here is how our one works. Basically, on one side, we have an energy plane, which is filled with PMTs, and on the other side, nearby the light production region, we have a tracking plane filled with silicon PMs. So basically, when an ionizing particle goes through the detector, it produces a prompt scintillation, which is detected by the energy plane, even as the start of the event. And at the same time, ionized electrons will drift towards the anode. There we have a high field, so we produce more light through electroluminescence. This light is detected also by the energy plane, which gives us the energy measurement, and also detected by the silicon PMs, which, thanks to being so close of the light emission point, allows us to do track reconstruction. We have been running the XY detector, which is the first underground phase of the experiment in Canfranc, from October in 2016 up to a couple of months ago, to July of this year. which basically was a 50 centimeter drift TPC with 40 centimeter diameter, holding around 4 kilograms of xenon at 10 bar. It was a kit with 12 PMTs for 30% coverage and almost 2,000 silicon PMs separated by 1 centimeter. Our goals were to validate the technological solutions in a large detector, to measure the background for future detector iterations, and to do a measurement of the 2 neutrino mode of the decay. And the topological signature is one of the great assets of NEXT, as it allows us to improve our background projection. Basically, thanks to the fact that we're using gas, the tracks are long, and basically go scattering all the way through the chamber, so we can study the event topology. We define two main observables, which are the blob, which is a dense energy deposition at the end of an electron path corresponding to the Bragg peak, and a track, which is basically a continuous energy deposition. So here you have a signal example, a simulated signal example. You can see a long track, which ends up with two high energy depositions corresponding to each of the two electrons. On the other hand, background events usually will have more than one track, more likely than the signal events, but even if they have a single track, they will look more like this. So they will start with low energy and then top with a high energy blob. This fact allows us to distinguish between signal and background by choosing events with only one track, and even when background events have only one track, you can look at the energy deposited at the extremes to distinguish between signal and background. Here you could see the distribution of how the energy at both extrema will look for signal events and for background events. It's clear that you can apply a simple threshold to distinguish background from signal. Our previous reconstruction relied on the raw silicon PN signal for obtaining the charge distribution. In concrete, we were using 2 microsecond slices, and each of the sensors was considered as an individual hit for later steps in the processing. Here you can see an example of how that would look like. However, this has a couple of shortcomings. First, our image binning was defined by the silicon PN pitch, which in our case, it was 10 millimeters, giving us a pretty coarse image. On the other hand, we didn't take into account any smear effects. In NEXT, due to a couple of issues, the signals are smeared, the tracking signals. On one side, we have electron diffusion. So electrons going towards the anode will diffuse and blurring the signal. Here you can see an example of a 40 centimeter drift at 10 bar. On the other hand, from the light emission point to the sensor position, light will also smear, blurring even more the signal. However, the Richardson lucid convolution provides a tool for us to solve this. So the underlying idea is basically that the image that we observe is a result of an original image, which will be this, for example, that is blurred by a kernel and additional noise. So basically, we are observing this image here, the third one. Richardson lucid, what it does is that if you know the blurring kernel, you can solve the inverse problem iteratively and get an approximation of the original image. So basically, in this case, if we apply the Richardson lucid convolution, we would get this image, which, even if it's not perfect, is much closer to reality than the observed image. To apply this in NEXT, however, as I said, you need to know the blurring kernel. So basically, we developed a method to obtain it from our data. We can obtain it thanks to the use of krypton, which we continuously flow into our chamber. Krypton 83 basically is around 40 kV energy deposition, which at 10 bar is basically point-like, and it's a gaseous source, so it's distributed throughout the detector volume. So if we evaluate what's the average fraction of photons detected at each given distance from the event origin, we basically get the PSF. What we do then is basically obtain a PSF for each 25 microsecond drift interval, which we deem to be the diffusion impact within each interval was deemed to be low enough. Each of these PSF will describe a fixed spread, which is the light spread due to from the EL to the sensor position, which is the bottom right one, here you can see. And then the rest of the PSF will also take into account the drift time. You can see here, for as long as you go farther from the anode, how the PSF gets wider and wider. This, incidentally, also allows us to get an idea of the diffusion and measure it for different sets. But okay, what we can do with a 2D PSF? So basically what we do is 2D deconvolution. This is good enough for short events, and we can basically apply it to the integrated signal. Here you have a couple of events. So we start with the raw silicon PM response. We will interpolate it to move to a more continuous initial seed, and then we will deconvolve it, getting a much sharper image. But in addition, what we have also evaluated is the resolving power that we can get through this methodology. So basically what we did is getting 2 random krypton events that were close enough. We added their response to create a synthesized response that counting for as if they were happening simultaneously. Interpolated them, so you can see there is no clear indication of 2 krypton events at all, and then we deconvolve it, and you can see the positions that are clearly identifiable, demonstrating the resolving power of the technique. But okay, short signals are nice, but what we are really interested is the long 3D tracks that we of the characteristic of the several MeV electrons. So to do so, what we do to use a 2D PSF to reconstruct these tracks is basically we slice the signal into microseconds interval. So this is our event, a projection along set of our event, and we basically apply cuts along the signal, which you can see here in the projection is in SY. And what we do is we apply the method to each of these slices. Here you can see an example after 2 iterations, 10 iterations, and 75 iterations. Then what we only need to do is to join them together to get this much nicer signal and much clearer for analysis. Here I show you a couple more events, 2 events of electron-positron pairs, which mimic the double beta signal, and a couple of background events. This is before the convolution, and here you have the much nicer result after deconvolving them. Once we have these hits, we basically voxelize them in larger cubes to maximize continuity, and we look for the track ends and characteristics using a breadth first search algorithm. Basically, we define the track as a group of connected voxels, being the endpoints, the points which have maximum separation along the track path. And revolving around those endpoints, we define spherical regions of fixed radius that give us that are defined as blobs, being the energy, the integral of all hits within the blob. Here you can see a comparison of the old reconstruction with the new one, and you can see how the much better resolution from the new reconstruction allows us to better identify the blobs, which before, in this case, they were pointing to an independent track instead of 2 tracks as we identified. To calibrate our methodology and to evaluate the background suppression derived from the technique, we look at the electron-positron pairs produced by the 2.6 megaelectron volt mass of thallium-208. Basically, they produce a 1.6 signal, which mimic our beta-beta due to having also 2 blobs. What we do is keep events in the region of interest, in this case around 1.6, and we optimize the reconstruction parameters to maximize a figure of merit, which we defined as the signal efficiency divided by the square root of the background acceptance.
We're about 10 minutes in.
Okay, thank you. The efficiency we define basically by the number of events that survive the topological cut and by the total number of events. So this will be the survival distribution after topological cut, but we need to count how many events are surviving. In Monte Carlo, we can basically take a look at what is the origin of the particle, but in data we need to think about how to do it. What we do is basically we do a fit to the energy distribution. So we have an expression an exponential to describe the background, and a Gaussian plus a step function to describe the signal. And what we do is we do a fit and integrate those functions around the peak region to get the number of background and number of signal events. Once we do so, and we evaluate the efficiency of the background projection, we get these results. In blue and orange, you have the results of the convolution after the fit. In green, you have the result of the convolution by counting real events. And in red, you have the old results that we had. You can see that we managed a great improvement from the old results to the new, and that the data Monte Carlo are really close together. In concretely, we passed from a 20% background acceptance to a slightly below 4% background acceptance without harming too much the signal efficiency. we have evaluated what was driven the enhancement, and we identified that we had an improvement point location. Here you can see the distance between the real endpoint position and the reconstructed endpoint, according to Monte Carlo. You can see we reduced the location error by 5-6 millimeters, and this has led us to a strong improvement in the measured blob energy. Here in orange, you can see what the blob energy solution for the lower energy blob looked like. And in red and green, you can see what looks like after the new reconstruction. In blue, you have what it should look like according to true information. So basically, what you can see is that we are much closer to the original distributions, allowing for a better cut when you look at the blob energy. In this sense, we still think the endpoint position can considerably be improved. You see there's not a small population which have large location errors, which basically are terribly wrong identified. So we are looking into ways of improving on that. We think that our current track reconstruction scheme relies too much in heavily voxelized data. So we are exploring new track reconstruction schemes that may take advantage of the continuity of the images, such as clustering or neural networks. We're also evaluating how to implement the convolution in 3D, because we are not taking into account any longitudinal diffusion effects, and the impact of those will rise in larger detectors. The problem with those is those are computationally heavy, but in that sense, we are evaluating modified algorithms to speed up the convergence. So to sum up, I just want to make clear that even if we have signals next that are impacted by the blowing effects, we have found a solution for them thanks to Richard and Lucy. And in the way, it allows us to completely characterize the optical response of the detector. Overall, our background acceptance has been reduced from 20% to 4%, yielding a five times improvement from what we had. And we have found that the improvement is driven by a better accuracy at the endpoint location. In that sense, we hope to improve, as we have already identified events that really fail.
Thank you so much. Are there any questions for Ander? So I was going to ask a question about the reduction of efficiency from 72% to 56%. What do you do to compensate for that? Just take data for longer?
I mean, yeah. No, actually, that doesn't worry me too much. If you go into events, it seems that there are some cleaning cuts in the analysis that may cut the track a bit. So you could recover them with smarter analysis.
With further analysis, you said?
Yes, with smarter analysis. Taking into account proximity criteria, you may be able to identify artificial cuts created by the process.
Understood. Thank you. Thank you. Are there other questions for Ander? If not, I'm going to move on to the next speaker. Thank you again for the great presentation. This is a very exciting session. So the next presentation is by Pietro Giampa, and he's going to talk about neutrino backgrounds in future liquid noble element experiments. Pietro, are you ready? Yes, I see your slide, and I can hear you.
Fantastic. Thank you very much. And thanks for the organizer for the time. Yes, today I'm going to report on a project that I embarked with two colleagues of mine, Andrea Gasper, who's now a graduate student at Stanford, and Dr. David Morrissey. I was a research scientist at Triumph. And the work presented here is in the archive that I posted here on the page. While I show you the overview, really what I want to present today is that we wanted to develop a new model to include detector effects and profile over the uncertainty of both the neutrino fluxes and some of the other parameters to really investigate the discovery limit or so-called fuzziness of the neutrino floor for future liquid noble detectors. So let's quickly set the stage for this work. In here, we have considered a signal that is mainly a WIMP-like dark matter particle scattering off a nucleus where the differential scattering rate is proportional to the cross-section and the dark matter flux. And in this particular work, we have adopted the dark matter halo model recommended by your community members, most of which are in the attendance back in May. And for backgrounds, we have considered solely neutrino backgrounds. In particular, we started with the covariant elastic neutrino nuclear scattering, where the differential scattering rate is proportional to the cross section in the neutrino fluxes, and this is really where the bulk of the project really was, and understanding the impact of the uncertainty of these fluxes. But we didn't want to limit ourselves to just sevens. Ultimately, this detector, especially as we look to bigger and bigger scales, they do have a finite ability of distinguish between electronic interaction and nuclear interaction. So we also wanted to model the neutrino scattering off of electrons, for which the scattering rate is proportional to the neutrino flux again in the cross section. But in here, we moved away from the free electron model, and we actually included atomic effects to account for the strong nuclear forces that bound some of the inner tight shell electrons, especially for xenon. I don't have time to dig into that modeling, but it's reported in the paper. Now that we have set stage, we wanted to introduce a detector model so that we could also characterize features of properties of detector and understand the impact on the discovery limit or neutrino floor of it. So we model each liquid noble detector, both in xenon and argon, by starting modeling the nuclear recoil energy resolution. For xenon, which is shown here on the left, we have assumed a resolution similar to what achieved by LUX and xenon 1 ton, so current generation. So we assume that the next generation will sort of follow the performances, especially for experiment that combine S1 and S2. And on the right-hand side, we show the equation for the nuclear recoil energy resolution that we effectively took from the D3600 experiments as a single-phase liquid noble detector. We also model all the way down to the quenching correction so that we can compare apples to apples for nuclear recoil and electronic recoils as we account for scattering off the electrons. And since this is a liquid noble conference, I wanted to point out that we performed our own, we followed the path that was done in NEST. So we modeled, we did a data driven model. And so we performed our own independent fit over the data that were in the parameter range of field ranges that we considered. And we have ended up with the quenching distribution showing cyan here. So once we can model the nuclear recoil energy, this was kind of important because it enables us now to set use the energy resolution to set the binning for statistical analysis as we go in later. And so we can simply rearrange the equation above to then set the binning size based on the resolution for the statistical model. Once you have everything, we sort of put together into a single equation for the differential scattering rate, where the scattering of WIMPs and sevens are combined together and scaled by a nuclear acceptance. And then the scattering of electrons of neutrinos of the electrons get scaled by the electronic rejection power of each experiment. So now that we have the signal and background, we have a detector model, we can start looking at the neutrino fluxes and the main component that comes in. So as far as we can tell, this is the most up-to-date pictures on the left of the neutrino fluxes as a function of neutrino energy. And so when you compute the center value with the equation showed above and the method showed above, you can look at the differential rate as a function of recoil energy and for both xenon and argon. And for reference, we have put also free lines from free WIMP-like candidates with a cross-section of 10 to the minus 48 centimeters square. And you can see immediately that for the, especially the region of interest that we look for the next generation of detector, the most important neutrino background in WIMP-like searches with mass above 10 GeV really comes from atmospheric neutrinos that have an uncertainty of about 20%. So it was important to build a statistical method that will enable us to profile over there. So here's the method that we put together as a standard energy bin likelihood method, likelihood function showing here, where Ni is the number of events in each energy bin, P is the Poisson distribution, and LB is the background likelihood function that is a product of independent Gaussian as shown here below. Once we have that, we calculate our test statistic, where eta and theta are the parameters that we use to maximize the unconstrained likelihood function for a data set Ni. And once we have that, we can just simply come up with our discovery limit definition, which is we can compute this for a set of experimental parameters that correspond to the smallest cross-section for which the experiment can exclude the background only hypothesis with a free sigma 90% of the time. So it's a standard free sigma sort of definition if we go parameters, again, reported in the paper more likely. So now that we know what is a signal, what is a background, now that we have discussed kind of how we model the detector response and show the both kind of what we're up against with the neutrino fluxes and we have our statistical method, let's take a look at what some of those discovery limits look like for a couple of example future-like detectors. So here's what the discovery limits look like for a xenon detector, an argon detector in a parameter space of cross-section as a function of mass, where the WIMP mass, where the z-axis corresponds to the exposure. And here we have taken two examples, what we call a Darwin-like experiment and an Argo-like experiment. So the Darwin-like experiment is a dual-phase xenon TPC with an ROI of about 5 to 35 kV, and nuclear recall acceptance of about 50%, and an electronic recall rejections of 2 × 10⁻⁴. This is really, from what we gather from a presentation that we found online and conversation we have with a collaboration member, a sort of target for a Darwin-like detector. But ultimately, as I showed you before in the slide before, if you want to compute for different configurations or you have a different model with different field settings and whatnot, you can just simply plug back in and then repropagate through. For argon instead, we chose a single phase argon detector with an ROI of 55 to 100 kV, nuclear recall acceptance of 90, and a electronic recall rejection power of 10⁻⁸. Now we simply picked single phase because we did the dual phase and xenon. As far as we can tell, there hasn't really been a decision in the argon community on where to move and for future large scale detectors. So please don't take this as a statement on that regard. If you would prefer to compute it for a dual phase TPC, again, we can go back and we go through the model and compute it. So as we mentioned, the dominant source of backgrounds from the neutrino side comes from the atmospheric neutrino fluxes. So here, what you see is the neutrino floor computed for the dual phase xenon TPC and single phase TPC, where each line corresponds to the discovery limit for each exposure in ton years. And here we have represented the solid line corresponds to a discovery limit calculated with a 20% uncertainty, profiled over with a 20% uncertainty in the flux. The dotted line corresponds to a 40% and the dashed line to a 10%. Uncertainty. However, I find that showing the neutrino floors and especially understanding the impact and the fuzziness of some of those dominant sources in this sort of parameter space is somewhat misleading. So what I'm going to do is I'm going to take a snapshot of 3 different masses, and I'm going to represent this in the cross section as a function of exposure for 30, 100 GeV and 300 GeV mass. And so here you really start, you really immediately by eye see the effect of the so-called neutrino floor. So at the beginning, when we don't have any impact from neutrinos, the discovery limit sort of scales up with the exposure. Then once we start seeing the neutrinos, we're limited by the systematic. So the discovery limit flattens. And then eventually you beat down the systematic and you limit by statistics. So your sensitivity scales with the square root of the exposure. And in the case of atmospheric neutrino, we see that reducing the uncertainty really will become crucial in beating down, especially for a future detector. And we also wanted to point out that updated calculations on the flux as a function of time and location will also be extremely helpful. And we elaborate in the paper more on the impact of the shape as well, not just the uncertainty on the flux should be considered when developing this. The next step was to consider the impact of detector parameters. And for that one, we focused on the electronic rejection power. In the world of argon, because of the 10⁻⁸ assumption on the rejection power, the effect here was really minimum. So we focused on understanding whether this was an important factor for xenon. And so we computed the neutrino floor for with a center value of for 3 different electronic rejection power, 2 10 to the -4, which seems to be more of the goal set for Darwin, and sort of 2 more conservative option of 1 10 to the -3 and 2 10 to the -3. Our results really suggest, as you can see in the plot below and the plot on the right, especially of discovery limit as a function of exposure, our results really shows that the current detectors and the current generations and the next generation of xenon detector should be able to handle with this rejection power the neutrino background. However, this is only true up to about 300 ton-year exposure. Beyond that, the recoil rejection starts to become a concern. And here is also where the importance on understanding the uncertainty on the shape of the flux might also become important. Finally, we asked ourselves more of a technical question, more of a theory question. Let's say if you live in a world in which the two experiments—
We're at 12 minutes, sorry to interrupt.
Yep. If we live in a world where we're running both experiments, both a xenon experiment and an argon experiment, and if we look at the next generation and we see this sort of about 10 difference in mass of about a factor of 10 between the two, we say, imagine that if we can run those and we're not limited by the systematics, we asked ourselves the question, what will be the gain if we could profile over both of them by combining them? And what we observe is that the enhancement at the next generation is minimal. However, it's present. However, what is striking is that if we're not limited by systematic, combining experiment, again, just by assuming a ratio of 1 to 10, you could effectively walk past the neutrino floor, and it would be a potential brute way to get past the flatness in sensitivity of the neutrino floor and continue beating down on the sensitivity. So that was quite surprising for us, and we just wanted to point that out. And with that said, let me quickly wrap up. So we presented this new energy bin profile likelihood method to estimate dermatodiscovery limits for neutrino backgrounds, including electronic interactions, and the ability to test both detector parameters and profile over the uncertainty of the neutrino fluxes. We have seen that atmospheric neutrino fluxes, because of their uncertainty and their energy range, will dominate the fuzziness, let's say, of the xenon and argon neutrino floor for the next generation of detectors. We have seen that the projected ER rejection powers for future xenon experiment shows that they should be able to handle this source of background easily. But this picture may change for very, very large exposure, possibly even beyond the capability of dual-phase TPC. And then finally, if systematic uncertainty can be controlled, our results also indicates that it may be possible to reach beyond the so-called neutrino floor by combining data from even larger argon and xenon experiments. And with that, I want to thank you, and I'm open for questions.
Thank you. This is a really exciting talk, and more arguments for having several targets. Matthew has a question.
Thank you. That was a great talk and really exciting new work. I have a question on the modeling of the yields down to low energies, though. So on your slide 4, it looked like you were looking at the overall quenching factor on the total quantum xenon argon, but how do you account for the division of labor there into the anti-correlated light and charge channels when, for nuclear recoil especially, the light yield has significantly worse uncertainty, and that drives the energy threshold more than the charge yield, which is a little bit easier to measure?
Yeah, so that's a very good question. Thank you, Matt. So in this work, as highlighted in the paper, we effectively took the center value. We were more focused on seeing whether this effect would change within the region of ROI, or if they were flat or stable. So we just simply took the center value, but I agree with you that there is more knowledge and input that we can put in there to more accurately model, especially at lower energies, these effects. But for the scope of this work, we figured that going with the most simplistic approach and the center value was at least a good first step, and then people can build up from there.
Thank you again for the great presentation. Maybe we can move on to the next presenter. Matthew, are you satisfied? Your hand is still up.
Yeah, I wish they installed a timeout for that on Zoom, sorry.
Yeah, that would be good. I agree with you. So the next speaker for this session is Pablo Amedo, who's going to talk about neutral brainstorm calculations for TPCs. Pablo, are you ready?
Yeah, can you hear me?
Yeah, we can hear you and we can see you and your slides look good.
Okay, that's okay, it works. So my name is Pablo Amedo and I'm a PhD student and at the Galician Institute of High Energy Physics, and I'm going to talk about neutral brainstorm in time projection chambers. The outline of my talk is going to be this one. First of all, I'm going to show some experimental evidence of this, then discuss what this is, the theory and how to compute it, then show results for gaseous phase, mainly, or especially comparison with experimental results, and then results for the liquid phase, which are mainly simulations. So I guess everybody is familiar with electroluminescence, but I will start the talk there. So when you have a bunch of electrons drifting in a gas, a noble gas in this case, if the electrical field is applied is high enough, you can excite the atoms of that noble gas that decay through different pathways, which gives you light, which is electroluminescence, which is proportional to the reduced field. Usually, this is thought to be a threshold-like process, where if you go to below a certain reduced electrical field, you no longer get electroluminescence. But if you zoom in this small region over here, you can see it in this plot, with, which are measurements in xenon. You see the electroluminescence region, and it becomes smaller, the electroluminescence as you reach, as you get closer to the electroluminescence threshold. And when you get below it, effectively, it begins getting smaller and smaller, but it doesn't outright disappear, since there are still enough electrons to excite some of the xenon atoms. But when you go to even lower reduced fields where no electroluminescence appears in any simulation, you can still detect some light, as you can see here. There was also experimental evidence of this by Luskov and collaborators a couple of years ago in Argonne. And with the aim of understanding this and trying to predict this scintillation below threshold, we found with this neutral brainstorm. Essentially, if a regular brainstorm is the emission of a photon by an electron that interacts with the nucleus or the Coulomb field of the nucleus, you can think of neutral brainstorm as the emission of a photon by the electron that interacts with the dipole field of the atom. In this simple approach, you can calculate the emission cross-section, just thinking of the incoming electron with a defined momentum and energy and a certain wave function, and then going out with a different wave function, energy and momentum. So in this cross-section, the most difficult element to compute is the matrix element. As you can see here, performing the full calculation is quite hard, so you can resort to the partial wave methods to simplify this and staying at low energy, so L equal to 0 and L equal to 1. And this allows you to simplify this calculation a lot. And if you carefully pick those first two functions, so 0 and F1, you can arrive at this result for the cross-section, which is what we are going to use to compute the yield for this process. So, yeah. So once you have it, it's quite straightforward to compute. You just need to plug it in these integrals and weight it by the energy distribution, the drift velocity of the electrons, and integrate over all the possible energies. You still need the energy distribution. So for that, we get it from Monte Carlo electron transport code, which is pi-volts. You can see here some results from pi-volts and Mach-volts and data from a certain gas. And here it's one of the energy distributions that we plug directly into this calculation. So once you have this, the only thing that's left to do in order to compare with the data is to plug in the geometrical efficiencies and the quantum efficiencies of the detector. So once you do all this, the result is as follows. This is the same plot as before. You get the electroluminescence region that starts decreasing as you approach the threshold, and below a certain region, it falls completely and disappears. But this time, the Neutrino simulations fit quite nicely the data where the electroluminescence is not able to. And it even allows you to describe the intermediate region where both contributions, electroluminescence and Neutrino have a similar order of magnitude. And when you combine the two of them, you can describe the full set of data along the full range of reduced electrical fields. So we wanted to test this a bit further and to really check whether or not this was actual Neutrino. So some measurements were performed with xenon and C2H6 at 0.12 molar concentration. As you can see here, again, in the lower region below the electroluminescence threshold, you are able to describe it just with the Neutrino simulations, but the electroluminescence simulations are not able to describe the electroluminescence region. This happens because you need to actually add quenching to the simulation, which this means is that in a really simplified scheme is that usually you have an excited dimer of xenon that decays this way, which I guess everybody's familiar with, and it gives you photons that you can measure. But if you have an additive in the measure like C2H6, this xenon can interact with it in many ways, which effectively steals some potential light from you. So it actually quenches the reaction. With a really simple model like this, you can calculate the probabilities for the quenching, and in our case, again with a really simplified model, we get a probability of scintillation of 0.37. And going straight into the data, the probability would be 0.55, which, although it may seem a bit different, there are quite some unknowns that go into these models, because you have to assume different rates for the pathways and all that. So it's considered quite a decent agreement. But the main point I would like to show here is that while you need to add quenching to describe the electroluminescence in your simulations, because you are losing some of the light to these reactions, you do not need to add quenching to the Neutrino simulations, because what this proves is that it's not an asymmetric base emission, because it's not being quenched by the additive. It's actually the electron radiating when it collides with the atom. So once we were sure that, well, this was a real result, we decided to dig a bit further into the small theoretical framework. And for example, we developed some simulations for other gases, as you see, krypton and argon, and also for other mixtures of noble elements. Well, it's worth mentioning that this framework only works when inelastic reactions are not dominant, so mixtures of either pure noble gases or weakly quenched gases, as the xenon C2H6 you saw. And we can easily decouple this calculation. As you hear, we have to run simulations for the mixtures because the energy distribution of the mixture is needed, but you can decouple the calculation of each of the elements, like you can see here. And here you can see several of those simulations, mainly xenon, which is the thicker line here, and then xenon argon, xenon krypton, which have a higher effect of Neutrino australum, and then xenon helium several concentration. Which is important here is that with these different mixtures, it allows you to either enhance or suppress the effect. Usually, I guess you are interested in suppressing this, and this goes nicely in line with some proposals in the literature, for example, about using xenon helium gases for TPCs to improve drift parameters without sacrificing too much light. This would also suppress this effect that can, for example, contribute to your backgrounds. So once we did this, we turn our attention to the liquid, because, well, there are many TPCs with novel liquid elements out there. So we thought that maybe we could predict the same Neutrino yields in the liquid. But for this, you need obviously cross sections that you can plug into the Monte Carlo calculation. And we found some that were calculated from first principles in the literature that you can see here. This is essentially the gaseous cross momentum transfer cross section, the blue line. And when you add some corrections of screening potential, you get this. And then when you add structure effects or well, the coherent scattering effects, you get this blue cross section here. And this one in the papers gets plugged into a multi-term solution of the Boltzmann equation and gives you these nice results over here. The units are mobility against reduced electrical field, but the main point that I want you to focus on is that this describes really nicely the data for liquid xenon and gaseous xenon. So with this set of cross sections, we decided to run our simulations. And we essentially model the gases as, the liquids as dense gases with the momentum transfer cross sections. And here you can see the results. These are
10 minutes. I see
okay,
you're almost done.
Okay, yeah, these are some of the results compiled from literature. And here are the results of our Monte Carlo. Here, I want you to mainly focus on high electrical fields, where there's quite a decent agreement between our simulations and the multi-term solution. There is a discrepancy at low fields because we are not including the medium effects that mainly take place at low energies. We are working on it, but so far at high fields, it's a quite good result. And this is the most important part, as you will see in a second. Here are the results that you can see. Scaled for, well, you can see both the gases and the liquid for each of them. So liquid xenon, gaseous xenon, liquid argon and gaseous argon, and liquid krypton and gaseous krypton. They are scaled by density, so they can fit in the same plot. And again, the most interesting part is the part of the high fields, because there's a convergence between, or they tend to be convergent for the different gases and liquids, which again is the region that we believe is better described by our simulations. And here you can see the three liquids, the calculation for the three liquids, and the breakdown voltages of liquid xenon and liquid argon as found in the literature. The main takeaway message from this, I would say, is that the yields, even below these breakdown voltages, are predicted to be significant at high field. So, for example, around here. And we even did some calculations in a paper that's submitted to PRX with from different experiments and different regions of these experiments, what kind of light from Neutrino they would see. And for example, this is quite decent for the buffer region in next. So conclusions, the experimental results for gaseous xenon simulations are quite good agreement, I could say, pointing towards Neutrino as the source of this light at low reduced electrical fields below the electroluminescence threshold, and simulations for mixed noble gases and quench and weakly quench mixtures predict enhancement or suppressive density on the mixture. So it allows you to fine-tune this effect. And then again, simulations for the liquid predict significant yields at high fields. So this is everything. Thank you for your attention. So I'm happy to answer any questions if there are any.
Thank you, Pablo. Thank you for the great presentation. Are there any questions from the audience? Maybe I can ask two that hopefully will be quick. One is, when you upload your code to GitHub, can we put in any arbitrary mixture of gases and see what happens?
Ideally, yes. There's only one issue though, which is what I mentioned here, which is this is mainly valid when inelastic reactions are not dominant in your gas. But otherwise, yes, it's possible to plug in theory, any mixture for which you have cross sections and see what happens, since it's pretty easy to calculate, I could say. Again, it depends on how dominant those inelastic reactions are.
There is another question from Sergey.
Yes, thanks. Were you calculating spectrum of this radiation? Is one question, and another, does it have effect? Has significant effect on electron drift and of drift of electron and electric field in gas or liquid?
You mean in the drift properties?
Yeah.
We are not sure of that yet. We are working on implementing this in a Monte Carlo simulation inside Bibles, so we can, well, besides fully integrating it into the code, and that will also allow us to predict whether or not this is relevant for the calculation of drift parameters. Because nowadays, you actually just run the simulation to get this kind of energy distributions. And then from this, you calculate the yield that it produces, but you are not able to see the impact on the drift parameters. I hope we will be able to see that once this is done in a purely Monte Carlo way.
Yeah, another question was about spectrum of radiation.
Yeah, we also calculated the spectrum. It's not here. I didn't have enough space to put that, but it's in the paper. It's actually one of the first figures. So if you are interested, I can send you the figure offline, but well, it's literally the first figure in the paper. Yes, it's the spectrum. So the photons emitted per different wavelength.
Great, thank you, Pablo. Let's move on to the next speaker. And the next speaker is Andrea Messina, who's going to talk about the luminescence of helium CX4 mixtures for the signal detector. Andrea, are you ready? I see you.
Yeah. I'm sharing my screen. Can you see it?
Yeah, looks great.
Okay, let me put it full screen. So now you should see it. So first of all, I would like to thank the organizers for the opportunity to present a study on the electroluminescence in helium CF4 gas mixtures for the Cigno detector. Okay, so let's start introducing the Cigno project. This is a project aiming at developing a large detector for high precision reconstruction of low energy nuclear recoils. As we know, this is a very challenging task because the rate is tiny. We have to carefully reject the background and keep the energy threshold very, very low. Our strategy to achieve this goal is to actually photograph the nuclear recoils, and we want to photograph these nuclear recoils that take place in a helium CF4 gas mixture. And the detector would be a TPC, which has a gem amplification stage to amplify the charge signal. And actually, in this stage, also light is produced. And our idea is to exploit these lights by taking a picture of it with a CMOS camera. You can see here two pictures, one of a soft electron and the other of a energetic nuclear recoil. Using also a PMT, we can have a 3D tracking and position reconstruction, and this allows us to visualize the events and measure the total energy released. The plus of the optical sensor is that we can have a high granularity with a very low noise and high sensitivity. And also the optical coupling allows us to read out a large volume and keep the sensors outside the sensitive volume. So let me briefly go over the Cigno timeline. So this is a project that I started in 2015 with an intense R&D phase where we developed our initial ideas. We tested the gas mixture and the readout strategy. So we started with a small volume of 0.1 liter, and we arrived now at the prototype, which has a 50 liter volume that we call LIME. So this is our phase 0. We are actually finishing to assess the performance of this prototype overground. We are planning to take it underground at the Gran Sasso laboratories by the end of this year. And this would lead to our phase 1, where we intend to construct a demonstrator, a 1 cubic meter demonstrator to be operated and commissioned at LNGS. The final goal of our project would be to propose a larger apparatus of 30 or more cubic meter. So one of our prototypes is called Lemon, and this is a 24 by 24 square centimeter readout area for 20 centimeter drift. Here in the drawing, you can see the sensitive volume of the prototype, which is enclosed between the photomultiplier and the GEM station. Just behind the GEM, there is an adjustable bellow with a lens that allows us to focus the collected line onto the camera. So we are using an Orca Flash 4 Hamamatsu camera, which has a very low noise and high sensitivity, with about 80% quantum efficiency that nicely matches the spectrum of the helium-CM4 mixture. This is a picture of the apparatus, and finally here you can see 5 seconds of natural background as photographed by the camera. The energy resolution of this prototype is about 15% at 5.9 keV. And we collect something of the order of 500 photons per keV. So clearly, the photon yield is a key parameter for the resolution of our apparatus, and we wanted to study how to increase the light yield, keeping the detector stable. So basically, the goal of this study is to see whether we can increase the light, keeping the charge at about the same level. So to do this, we used one of our prototypes. So here you can see a cartoon where you have the 3 GEM station, and just below the GEM we placed a mesh such to be able to have an electric field after the amplification stage. So the mesh actually screened about 50% of the light and had a very good flatness, and this was very important for the stability of the measurement. We also used a glass ITO coated, we used a glass ITO plate, and this allowed us to have a much better detector stability and a better light transmittance. So by tuning the electric field here, we can study the charge collected and also the light produced. So we exposed this prototype to iron 55, and as you can see, by changing the electric field just below the GEM station, we clearly see an increase in light. So this is a long exposure pictures. Similarly, by just reconstructing the iron 55 spots, we can look at the photon in each of the spot, and you see that by increasing the light, the peak moves to higher number of photons per cluster. So this is our first demonstration of electroluminescence in helium CF4. So here we wanted to be a little bit more quantitative and comparing the light and charge yield with the electric field after the GEM. So you can see in this plot, as a function of the field behind the GEM, the relative increase in charge, these open bullets, and light. And you see that while the light increases by about a factor of 7, the charge increases by something less than a factor of 2. Taking the ratio at the maximum electric field, we have a light to charge ratio of about 3. Actually, using the ITO, we managed to go even higher in the electric field to about 17 kilovolt centimeters, and we arrived to an increase in the light yield of close to a factor of 25. So one thing that we wanted to study was the dependence of the amplification on the external field. So a test we did was to reverse the applied voltage on the ITO, keeping the gem stage at the same voltage. And what you see is that for positive voltage, you have a strong increase in light, while reversing the polarity, we get a reduction by about 10%. So clearly, this light is produced below the gem stage. To go even further in this, we wanted to study the behavior of light and charge as a function of the electric field in the gem hole, which is a combination of the voltage applied to the gem and the electric field below. So one test that you can do is to keep the same electric field and start changing the voltage applied to the gem. And what you see is a behavior in light and charge, which is pretty much the same. On the other hand, if you start varying the field below the gem, and you have a strong increase in light, while the charge doesn't increase so much. So this again is telling us that this light is produced below the amplification stage. So
we're at 11 minutes.
Yeah. Another test was to study the dependence of the total voltage applied to the 3 gems. And here, what you can see is that the charge yield depends almost only on the sum of the voltage difference applied to the gem. Doesn't really depend on which of the gem you are playing with. A similar behavior, you have it in light. And finally, if you start adding an electric field below, you start getting more light for the same configuration of the gem. So the light yield depends almost only on the sum of the voltages applied to the gem and on the field below the 3rd gem. So another study we are carrying on is to include isobutane. So the motivation for this is that including isobutane allows us to have a very light target, namely hydrogen. So with a very small percentage of isobutane, we get roughly the same amount of hydrogen and helium. And this is interesting for low mass dark matter. So the goal of this study was to study the charge and the light yield for this mixture. The apparatus is similar to the one described before. The only difference is that there is only 1 gem and not anymore 3 gems. We are able to read the charge and the light with the produced during an exposure to iron 55. So the results that we got increasing the isobutane up to 5% is that overall the number of photon per avalanche electron decreases, going from 0 to 5% by a factor of about 8. And this is a problem. However, the interesting thing is that we get about a factor of 3 increase in the maximum number of avalanche electrons. So at the end, the overall yield per absorbed keV is reduced by only a factor of 2.8, meaning that we are able to have a good light yield also with a mixture of isobutane. So this takes me to my summary. The Cigno project is developing a gem-based TPC with an helium CF4 gas mixture at atmospheric pressure, and this detector is read out optically. It has a good energy and position resolution, and currently we are working on an R&D concerning the increase in the light produced by this detector, and I've shown you that we are able to increase the light yield, keeping the charge almost at the same level by applying a field below the amplification stage. And we are also able to run with up to 5% of isobutane without degrading the detector performance by a large factor. So thank you, and I'm open to your questions.
Thank you, Andrea. Very nice talk. Are there questions from the audience? If not, I will ask the elephant in the room. Are you considering to use one of these type of detectors for potential low mass dark matter detection?
Yes. This is actually our aim. So now we're working on a small demonstrator, and this would be. Let me see if I have in backup. Okay, here we are working on a 1 cubic meter demonstrator, and this would be installed at LNGS. This is going to happen in 2022, 2023. This is not really competitive with the status of the art of low mass dark matter searches, but would open the road for a larger apparatus that could be quite interesting to search for low mass dark matter.
Thank you so much. This is very exciting. We're running a little late, so let's move on to the last speaker of today. The last speaker is, oh, I lost my page. Daniel Dornford, who's going to talk about nucleation efficiency of nuclear recoils in superheated liquids. I saw Daniel log in a second ago.
Yes,
and
hello.
I see your slides and I see you and I can hear you.
Perfect. Okay. Hello, everyone. Yes, I'm Daniel. I'm a PhD student at the University of Alberta, and today I'm going to be talking about measuring the nucleation efficiency of bubble chamber experiments. So the SBC collaboration is pursuing the use of scintillating bubble chambers to look for low mass dark matter and coherent neutrino scattering. In particular, we are currently fabricating 2 very nice liquid argon chambers for these separate searches. For all the details about that, see the slides from Eric Dahl from yesterday. But also just to give a 1-second sort of overview of how bubble chambers work. They use superheated liquid target medium to look for low energy nuclear recoil events. In particular, when you have an event in the liquid with a sufficient energy, it can cause a small cavitation, and then the resulting bubble can be observed optically or acoustically or barometrically. This process is also very highly suppressed for electronic recoils, which tend not to deposit their energy in a small enough radius. So they have a very strong natural background suppression. And PICO is an experiment that has been using this technology to look for dark matter for a while now. In particular, they use fluorocarbon bubble chambers. But the picture is pretty much the same for us at the SBC collaboration, except that we can also observe scintillation light that's produced inside the liquid noble target as well. And we're particularly studying liquid xenon and liquid argon. So in addition to potentially providing a means of energy reconstruction, that could also be very useful for further background suppression, since the scintillation yield for electronic recoils should be much higher. But one particular challenge that's faced by all of these bubble chamber experiments is understanding their nucleation efficiency. So as a function of the recoil energy of incident particles, what is the sort of threshold and efficiency curve with which you actually produce observable bubbles. And there is a theoretical model, the CITES model, that predicts a perfect threshold just as a function of the pressure and temperature of the liquid. But it's been known experimentally for quite a while that the reality is actually quite different. And there's no really good a priori expectation for what the shape of these efficiency curves should be or anything like that, although that is something we're working on. So really right now, in lieu of that, the objective is just to measure this directly with calibration experiments. And so this is actually the part of my slides where I take a pretty significant detour to talk about PICO specifically, even though it's not a liquid noble experiment. The reason for that is that this whole calibration technique that I'm going to describe was developed with PICO data. But I promise we'll get back to the liquid noble stuff at the end. So in pursuit of this goal, PICO has collected neutron calibration data with lots of different sources, including beam data and americium and antimony beryllium source data, all for a variety of different thermodynamic states. And then for each of these experimental setups, there is a corresponding Geon4 or MCNP simulation so that you know the expected flux of neutron events in that setup. And then by comparing the expected flux of neutrons with the actual observed number of counts for different multiplicities of bubbles, you can determine the nucleation efficiency curve. And so the basic idea was to do a joint fit for all of these different experiments and all this data. Specifically, the model that we used is a piecewise linear function for the efficiency curve, where these efficiency nodes are fixed. And then it's actually the energy at which you reach that efficiency that's the free parameter that can slide back and forth. We have one curve each for fluorine and carbon in all of this data, which was taken in C3F8. And then all of that is also for two sort of representative thermodynamic thresholds of about 2.5 and 3.3 keV. For all experiments that are not quite at either of those points, we do a linear scaling to the closest of the two. And so the likelihood function we have built for all of these data sets is just the likelihood for the observed number of counts for the ith experiment with the mth threshold, actually should be a m instead of a j there, and for the kth bubble multiplicity, and then sum together for all of those. Those four efficiency curves that we're fitting give us 20 parameters of interest. And then on top of that, we have 14 nuisance parameters that we use to account for systematic uncertainties that are listed in these tables here. That includes uncertainty on the thermodynamic conditions of the different setups, as well as on the source strength or beam strength, or uncertainty on the geometry as well. And so fitting a very highly dimensional model like that with 34 parameters is a little bit of a computational challenge. Definitely a Markov chain is a well-suited tool for this, but we decided to sort of take things one step further with what we call the fast burn-in technique. Essentially what we do is, instead of letting the Markov chain run continually, we interrupt it every 10 steps or so. We bin all of the samples explored in each parameter and then find the best fit points of those bins and use those as starting points for the next sort of iteration of this process, and then just keep doing that over and over again. And that's what's being depicted in this animation here. The blue points are all of the samples explored, and then the red points in each frame are those sort of reseeding points for each successive epoch, we call them. And so what this does actually is it really forces the Markov chain to explore the boundary of the likelihood function. You can see it's sort of concentrated around the edge of this plot. So this does sort of surrender, I guess, one of the key features of a Markov chain, being that the sampling is proportional to the area. But if you're just using the boundary of the likelihood function to estimate confidence intervals, this is actually what you care about. And so in that sense, it's sort of more efficient for this highly dimensional parameter space. So with this technique, we have this result for the PICO calibration data with efficiency curves for fluorine and carbon at these two different thresholds. This is definitely a key part of PICO results going forward whenever a WIMP exclusion limit is reported, for example. In this case, the fluorine curves are typically a much better constraint than the carbon, just because we actually had sort of on residence beam data for fluorine. But just leaving things at this stage was a little bit unsatisfactory to us, because we have this very interesting sort of ad hoc model fit to lots of very complicated data sets. all sort of untested with a sort of new and weird optimization technique too. So to sort of reassure ourselves of the robustness of this result, the next thing I did was a parametric Monte Carlo study. And by that, I mean taking the best fit model to the data, which is shown in blue in this plot, and using that to generate simulated data, which is all the little rainbow colored points. And then you just take those simulated data sets and you fit them with the exact same procedure as before. This can tell us a lot of things about the sort of validity of this procedure. The first and most obvious of which is just that this actually confirms that the convergence criteria we used in the first place was actually adequate, that the markup chain really had finished converging on the final result. This is just to show you what the fits of those simulated data sets look like. Most of them end up pretty close. But another really important thing we can do with this result is we can actually use it to interpret the chi-square value we get from our likelihood function as a proper goodness of fit statistic. That's not as easy as you might think it is, because a lot of the parameters in this model are highly correlated with each other. So the actual sort of effective number of degrees of freedom in the model is very different than you would expect. But by looking at the chi-squared for these simulated data sets, you can sort of estimate what the effective number of degrees of freedom is, which turns out to be about 46, and compare that to the chi-square value for the real data. And you can see we actually have a pretty reasonable fit. Another important thing we can do is we can compare the fit results for all the different parameters to the true value, since we know that for these simulated data sets, and use that to look for any systematic biases as a result of this procedure. And so in this case, you can actually see some very small biases in the fits. Like for example, for fluorine at 100%, the fit tends to return a value that's a little bit high. For carbon at lower efficiency, it tends to return a value that's a little bit low. None of these biases are significant, of course. They all, sort of overlap with the 1 sigma envelope of the original result. But now that we have this information, we can actually use it to produce bias-corrected results to report in green, shown here, compared to the original result in blue. And this is for the 2.45 kV threshold and then 3.29. So again, these, the difference is very small and entirely negligible in some cases, but this just, reassures ourselves that this result is just that much more robust. So a dedicated paper about all this analysis for PICO is coming out very soon, so definitely keep your eyes open for that. But now that the sort of technique has been proven, we can come back to the liquid noble side of things because we can apply pretty much the exact same methodology. So definitely when we have those liquid argon detectors, this is the sort of analysis we will do. But in the meantime, we do have some calibration data from our small liquid xenon test chamber that was operated at Northwestern a few years ago. Matthew Bressler gave a lot of details about that this morning. But what we have so far from this experiment is data from a californium source at 4 different thresholds, as well as the corresponding simulation of neutrons in that experimental setup. And then we can apply the exact same analysis as before. So I won't go through all the details again, because it's very much the same technique. But that gives preliminary results for liquid xenon that look like this. So for this experiment, we had thresholds from about 0.9 kV to 2 kV. In this case, the efficiency curves are definitely not as well constrained as I showed before, but that's just because we are dealing with a much more limited data set. And definitely when we include more calibration data from neutron sources, this result should get even better, but definitely very exciting to see so far. But that is all for me. Thank you very much for your attention, and I'd be happy to answer any questions.
Thank you so much. This was also a very exciting talk. Are there questions from the audience? So maybe I can ask one while people are thinking. If you go to maybe slide 12 and 13, when you do the bias study, you make a comparison in accuracy. Is there also a comparison in computing time that becomes relevant here?
Yeah, for sure. So, I mean, like I said before, one of the important results of this study is sort of confirming that the convergence criteria that we set to sort of automatically decide when this was finished, we wanted to confirm that that was valid. So in this case, actually, the computing times turned out to be pretty much almost exactly the same for the original and simulated data sets. We intentionally started from the same, maybe not, not great initial guess, just to make sure that it would take about the same amount of time. For that Pico analysis, it turned out to be quite long. I think it was about 2 months with 8 CPUs running in parallel, so quite computationally expensive.
You need a bigger computer.
Yeah. That's actually one of the nice things about this new analysis with Xenon, is because there's only one species of atom that we're dealing with, and not so much data so far. It actually ran, I think, about 3 days or something like that. So
that's better. Micah has a question.
Yeah, thanks. I was wondering, on slide 11, you have this graph of the infinite comparison. Are you getting like appropriate coverage on this as well? Can you check if your uncertainty estimates are accurate?
A coverage of the uncertainty. That's true. Actually, that is something else we could do, especially since for this we're just using this sort of Gaussian approximation for the likelihood function. I don't actually have specific coverage numbers for this. Because this Pico analysis was so computationally expensive, actually, I was only able to do this study with 25 points, with 25 simulated data sets. So I don't know if that would be enough really to be very convincing in terms of a coverage check. But again, like for the Xenon analysis, because it's so much quicker to do, we could definitely explore that with a much larger number of simulated data sets.
Cool, thanks.